Okay, class, welcome back. Today is lecture 7, and we are talking about systems of linear equations. And let's get started. So, first thing I want to remind you about is what it means for something to be a solution for an equation. So recall that if you have some sort of equation, you have an equation, I don't know, maybe like, how about something like this? X squared plus y squared equals 1. So not necessarily linear or anything, just any old equation. Then what does it mean for something to be a solution? So you say like x equals blank, y equals blank is a solution. What does it mean to be a solution? It means that they satisfy the equation together. Meaning that when you put the two numbers in, you get something that makes sense. So for example, x equals 1, y equals 0 is a solution because if I plug in 1 and 0 to this, I'll just add parentheses in now to make everything more clear. If I plug 1 and 0 into this for x and y, I get this becomes 1 plus 0, which is just 1. So I get something that is true, that makes sense. While, for example, x equals 1, y equals negative 1 is not a solution because it doesn't satisfy the equation, meaning that when I plug it in, I don't get something that makes sense. So in fact, I would get 1 plus negative 1 squared is 1 equals 1. So I would get 2 equals 1, which doesn't make sense. So that's just a reminder of what it means to be a solution. It also means that the coordinate is on the graph of the equation. So if you were to graph it, then 1, 0 would be on the graph, but 1, negative 1 would not be on the graph. Okay, so that's just a little reminder. So then what we want to do now is think about having more than one equation at once at a time. So we can also look for solutions. So up there, I didn't really look for a solution. I just checked something was a solution, but we can look for solutions too by solving for variables. And we could do this for more than one equation at a time. So that's what today is about. Today we'll stick with 2, but you could do more than 2 equations. So this is called solving a system of equations. And we're going to simplify our lives a little bit by only looking at linear equations, not any old equations in the world. So we'll only look at the linear ones. So that's why we call them systems of linear equations. So linear equations are ones that create lines when you graph them. So they always look like a number times x plus a number times y equals another number. And so we're going to look at more than one at the same time. Okay, so let's just jump into an example. That's the easiest way to just get the idea down. So let's do that. So we'll see things like this. Solve, and then when you want to write a system of equations, we use this fancy curly bracket notation, and we stick our equations in there. So our first linear equation will be 2x plus y equals 3. Our second linear equation will be 2x minus 3y equals -2. So it's a system of two linear equations, and we're going to solve it. So we're going to end up with some sort of x and y value. And what does it mean? Well, it means that the x and y value that we get, the pair, are going to work for both equations at the same time, not just one or the other. So that's the purpose. Okay, so meaning we're going to find all, that's what solve means, find all x, y pairs that satisfy both equations. So it's not good enough to satisfy one, got to satisfy both. And there's two main methods for doing this. So that's what we're really learning about today, is these two methods. The first method is called substitution. And it goes like this. You solve one of the equations, dealer's choice, whichever equation you want. Solve one equation for one variable. Again, dealer's choice, whichever variable you want to solve for. So that's going to be the first step. So let me just rewrite the equations down here. Sometimes I'll leave out that bracket because it just sort of gets in the way, and I'll just write it like something like this. Okay, so this is the system. So what we're going to do is we're going to solve one of the equations for one variable, and you sort of want to choose wisely. So it would be easiest to solve this for this y in this first equation, because all you got to do is subtract 2x to both sides. If you wanted to solve for x, it would be a little bit more annoying. If you wanted to solve the other equation for a variable, it would be even more annoying. So we're going to do this way. So you sort of choose wisely. So then the next step is to plug it in to the other equation. And what this is doing is it's ensuring that your x and y are related by both equations at the same time. So that's why we're going to be able to solve for a point that works for both equations at the same time. So now we are going to take 8x minus 3y equals -2, and we are going to substitute, aka plug in, this for y that we know is y in the other equation. So that's all we're doing there. Replacing y with what the other equation says y is. This way, both equations relate x and y together in both ways now. Or sorry, now we have one equation which does both. And then what happens is that we get an equation that only has x's, so we can solve this for x. Once we simplify. So we got to distribute this through -3 through to get 8x minus 9 plus 6x equals -2. And then we'll end up with, so if I add 9 to both sides, this will be a 7 over there. And 8x plus 6x is 14x. Divide 14 to both sides, and you get x is 7 over 14, which is 1/2. So this x value will correspond to a y value that fulfills together both equations once I plug this back in. So we plug this back in to get a corresponding y value, which solves both equations together. So which one you can choose either equation to plug x back into to solve for y, but you sort of again want to choose wisely. This guy already tells me how to get y if I already have x. So that's the one I'm going to use. Y equals 3 minus 2x. I'm going to plug in this x value of 1/2. 2 times 1/2 is 1. So you get y equals 2. So the solution is x equals 1/2, y equals 2, solves the system. And so you could ask, of course, is there more answers than just this one? Like, how do I know that this is the only answer? We'll get to that in a second. But right now, what I want you to think about is how you can interpret this, and that'll help us with the other question. Interpret, I don't know how to spell that. Interpret. That doesn't look right. We can interpret, spell it yourself. Okay, we can interpret this graphically. As the point 1/2, 2 being on both lines, because 1/2, 2 solves both equations. And since this point is on both lines, if you have two lines and they cross, then this must be that crossing point, is the idea. So since they can only cross once, like this, right? The lines can't like double back and cross again. Since they can only cross once, this is the only solution. So that's how we know that this is the only solution to the system. Okay. So let's do another example with the other method. So we'll do a new system, solve this one. It's a good curly bracket I drew, pretty good. 5x minus 6y equals -22. So the first method, substitution, is pretty good if you can identify one of the variables as being easy to solve for, and there's no like messy fractions going on. But if you do that here, there'll be some annoying fractions you'll have to deal with. So that's when this other method is really useful, and it's called elimination. So what we do here is, well, I'm just going to do it and then we'll see that it works sort of magically. I'm going to multiply the first equation. So at first it seems like magic, and then you'll see why I did it. I'm going to multiply this first equation by 3 on both sides. So if you have two things that are equal, which is what an equation is saying, that these two things are equal on the left and the right, then multiplying by 3 on both sides keeps that equality going, so it's okay to do. So I'm just going to take this first equation and I'm going to multiply both sides by 3. And it preserves them still being equal. So it's just writing the same equation in a different form. So we're just being sort of sneaky by writing it in a different form, because then the system becomes better somehow. And the payoff is only revealed once you get to this step. So the payoff is that if I just add both equations, so if I have two things are equal and another two things are equal, then I can add on both sides and they'll still be equal. And that's what we're going to do here. So I'm going to just add these two equations. So if I do that, then what happens? Well, on the left side, if I add these, 9x plus 5x gives you 14x. 6y plus -6y cancels to 0y. So this is the goal. And then these add up to -28. Why is this good? It's because now I have one equation with only one variable because there's no y's left. And this allows me to solve for x. So this process cancels one variable. And then you can solve for the other. So all I have to do now is divide by 14 on both sides, and I'll get x equals negative 28 over 14, which happens to be 2. And then once we have one value, either x or y, in this case we got x, and then we just got to do what we did before and plug it back in. So we'll just plug this back into either equation, and we'll get the corresponding y value that solves it. So it's your choice, whichever one. I'll just do the second one this time. So 5x minus 6y equals negative 22. I'll plug in x equals negative 2 there. So what is that? Negative 10 minus 6y equals negative 22. Add 10 to both sides, and we've got ourselves a nice y value here by dividing by this negative 6. So we get y equals 2. So the solution is x we had as negative 2, y equals 2, and also negative 2 comma 2 is the point where they intersect. Or where they cross. So that's elimination. Now, you don't always have to use the number 3. So now we can sort of look back and see why I chose to multiply by this 3 here. It wasn't just a random number. It was because I noticed that if I just multiplied this by 3, it would become the opposite of this number. And then they would cancel when I added the equations. Meanwhile, this 3 is a bit more annoying to make be 5. I would have to multiply by like 5/3 and also make it negatives for those to cancel. So the wiser decision was to turn the 2 into a 6 by multiplying the first equation by 3. But you could multiply by whatever you want on either equation to do a similar trick. So I'll do more examples later where we pick a different number. Okay. Right now, what I want you to remember for a second, just hold this in your brain, is that you can have the same equation written 2 different ways. And so this line is the same as this line written differently, secretly. They're the same line. And that's going to come back in a second here. Okay, so because what I want to do next is I want to describe different situations that could happen. So since linear equations create lines, when we graph them, we can see, just visualize very easily the number of possible solutions in different situations. So right now, situations, we've only seen one situation. And that's if this system has 2 lines and they cross at a single point like this. So this is the only solution because 2 lines can only cross once. But there are weirder things that could happen. So that's one case. What else could happen that's a bit weirder? You could have 2 lines that are parallel. Remember, that means that they have the same slope. And so these will never touch. So that must mean the system will have no solutions, because the system having a solution means all the points that work for both equations, and there are no points in common, so no points work for both. So we didn't see any examples like this, but we will in a second. So this system has no solutions. And then the weirdest one, perhaps, is if you accidentally have a system where both lines are secretly the same line. So it's a bit tough to draw, but basically I have one line in my system, and then the other line is actually the same line, you just didn't know it, and so they are the exact same line. So then what that means is every point is a solution because every point is on both lines. So every point on one line is on both. So there's actually infinitely many solutions because they all work. All the points that are on one line work on the other, so there's infinitely many solutions. So we didn't see any examples like this either. So let's see some of these weirder examples and how the system looks that correspond to these weirder examples. So what about this one? So this one, let's use elimination just for practice. Elimination. So what I'm going to do is I'm going to take my second equation here and I'm going to multiply it by -2 because I'm noticing that that will make this be the opposite of that one. So I'll be able to cancel the y's, but actually it'll also make this the opposite of that one, and I'll be able to cancel the x's. So we get 4x plus 2y equals 10, and -4x minus 2y equals -6 when you distribute this -2 to everything. So then we are supposed to add these equations, right? So what happens when we add them? Well, on the left, these add up to 0. They cancel. These also add up to 0 because they cancel too. -2y plus 2y is 0. And then over here we get -16. So we get 0 equals -16. So that tells us that there's no solution because we get something that doesn't work. So no x or y values will ever make 0 equals -16. So there are no x or y values that will solve the system. And so that must mean that the lines are parallel. There's no solution, they must never touch, since there's no point in common. And if you actually graph these, which we know how to do, you would be able to see that they're parallel, or you could just check their slopes, and you would also get that they're parallel by writing them as y equals mx plus b form. Then you would check and you would see that their m's are the same. Okay, so that's what can happen there. And now let's see the other weird example. 5x minus y equals 4. 10x minus 2y equals 8. So again, I'll do elimination just because that's the one that usually requires more practice. And in this case, I will multiply the first equation by negative or +2 this time. And if I do that, then the system becomes, well, the first equation becomes 10x minus, oh wait, I do want negative, sorry. So let's do that, -2 here. So then if I distribute it through, I get -10x plus 2y equals -8. And the other equation is 10x minus 2y equals 8. And what you might notice before we even add is these are actually the same equation. If I just multiply one of them by a negative, I'll see that they're exactly the same. So I'm not going to do that, but you could do that and you could see that they're the exact same equation. Instead, what people do is they just add the two, and what they get is 0 plus 0 equals 0. So this time you don't get 0 equals -16. You don't get something that doesn't make sense. You get something that always makes sense, always true regardless of x and y. And that's why there's infinitely many solutions, because all the x's and y's will satisfy the system. So infinite solutions, which also means that these are the same equation. They're just secretly written differently, which is the second equation is just the 2 times the first equation on both sides. So they're actually the same equation. So when they are actually the same equation is when you get infinite solutions, and you don't have to write them out or anything. But if you wanted to, you could say what they were, and they are just the points on the line. Points on which line? Well, this line, they're the same line. So you could write either one. So any point on this line is a solution to the system. And that's it. Okay, so now let's do some more. Those are the 2 sort of weird cases. Let's do a couple more examples of the stranger ones, just for more practice, or the more typical ones, just for more practice. Okay, so let's solve this one. So maybe I'll do a substitution here because I've done so much elimination. So substitution, I'll notice that this x looks very nice to me because I can solve for it quite easily. All I have to do is subtract this 4y over, and now I can plug this thing in for the x in the other equation. And then we get -2 times 6 minus 4y plus 3y equals 2. Distribute that -2 through, -12 plus 8y plus 3y equals 2. This becomes 11y. And then I'll add this 12 to get 14. So y equals horrible fraction. It'll happen sometimes, that's okay. So that's y. And how can I get x? I can just use that I solved for it in the first place to get it right here. So x equals 6 minus 4 times 14 over 11. Disgusting fraction. Let's just leave it at that. That's fine. You can simplify that x if you want. But that's the process. And if you do elimination, you'll get the same answer. So how could you do elimination on this one? I would say you should multiply this first equation by 2 if you wanted to do elimination, because then the 2x and the -2x will cancel when you add. All right, one more example, and that'll be it. A slightly more complicated example, just so you can see the most difficult possible situation. Well, I could make it more difficult by doing annoying fractions, but this is the most difficult yet not annoying situation. So let's do that. Okay, so something like this is a bit more annoying, a bit more difficult, because if I multiply this by, if I multiply the first equation by a whole number, there's no way to make the 2 and the 5 cancel. So I would really need to multiply by -5 over 2. And then I would get -5x, and then it would cancel nicely. But that's a bit annoying because I don't want fractions. So there's a better thing to do. How about instead, I just multiply by -5. And at the same time, I multiply the second equation by 2. So we can adjust both equations at the same time. So then what do we get? So on the top equation becomes -10x plus 15y, because I'm distributing this -5 through to everything, equals -5. And the second equation becomes Now I'm distributing this 2 all over the place. So that becomes 10x plus 4y equals -4. And now adding becomes a bit less horrible because I don't have a fraction. I'm not going to have to do a 5/2 to everything, which would have been annoying. So now adding is a bit more relaxing. Okay, now I'll just get this and this will add up to 0 when I add. And then this will add up to 19y. And this will add up to -9. Yes, we're going to get a fraction at the very end by dividing by 19, but that's unavoidable. But at least I didn't have to deal with fractions when I was trying to eliminate things. So that's going to be y. If I had instead decided to multiply the first equation by -5/2 as originally planned, you could see how it would be very annoying. This one wouldn't be so bad because you would just get -5x, but this one would be like 15/2y. Ugh, disgusting. And this would be -5/2. Ugh, I don't want to add those down because then I would have to add that and get common denominators and it'd be terrible. So let's not do that. Instead, manipulate both equations. And then when you add, it's nice and soothing. You get a nice cancellation. Okay, but now, yeah, we have to deal with a fraction. We got to put this back in. That's unavoidable. That's okay. So we can use either equation. I'll use this 2x minus 3y equals 1 equation. So then use this to get x. So we get 2x minus 3 times -9/19 equals 1. All right, yeah, terrible, but that's okay. I'll do this one. Plus 27/19 equals 1. So I got to subtract this 27/19 to both sides. So this 1, I'll write as 19/19 so that I can subtract properly. What 19 minus 27? What the heck is that? I think it's a -8. And finally, divide by 2. Now, you might be confused about dividing by fractions, but dividing by 2 is the same as multiplying by 1/2. So we could think of it like that. And then I can cancel a bit to get -4/19. So that's my x. And my y was -9/19 earlier. Solves the system. And that is it for today's lecture. So I will see you next time.